bit smaller. So it doesn't weigh then 2 kilograms, but it only weighs as much as the chip weighs, about 2 grams or slightly more. So it's really, then the heat sink has the same kind of scale that the chip itself has. So that's an important benefit. And the other benefit is that heat, once it is being absorbed into liquid, can be carried much more easy over longer distances. Air is difficult to transport. For example, a high-performance computer, a Blue Gene in its full size, will require half a cubic kilometer air per hour to cool. How do you get half a cubic kilometer air transported? So with liquid, it will be in much smaller volume. Now, I mentioned my background is biophysics, and we have been thinking, how can we use biological principles to improve the efficiency of computers? And the first topic was the system of arteries and veins, which we used, and we built in silicon technology such a system. So what is the virtue of this, our blood circulation system? We have a hierarchically branched system. We have one input, which is being driven by the heart, and then we have a branch system that eventually drives billions of capillaries. And the heat exchange and the mass transport, which is important for us, happens all in the capillaries. And they typically have a length of 100 micron and a diameter of 10 microns. And we now are able to use silicon technology, deep trench etching, to build capillaries of the same dimension. So it's standard microtechnology that can do that. And what you see here is a chip which is being cooled by a lot of these streams, and they are fed by two systems. And it's always important that we have two systems. We need a system to provide access of the fluid, and we need to have another system that drains the fluid. And two intermixed hierarchical systems are very complex to build. It's really, we have to see that there is no collisions. But it's possible using here a system that does a threefold branching in one dimension, in X, and a threefold branching in Y. So we have, per layer of silicon, we have a ninefold branching. And what we want to achieve is to drive 50,000 nozzles and capillaries per chip using one input. So we need about 4 layers of this ninefold branching. And then we can kind of implement the biological system. By the way, the biology prefers bifurcation, so always one channel is split in two. From a technology point, we calculated that trifurcation is the best because we're using right angles. If you really go into theory, then it turns out that about 2.5-fold branching is the most efficient. So biology kind of more went to the 2-fold branching, bifurcation, while technology will go to the trifurcation. But it's the same basic principle then that allows to improve the heat transfer, and that has been shown in technical papers. So the heat transfer we can reach with that is 350 watts per square centimeter. This is about 10 times more than a hot plate dissipates. Now we're working in this area to even increase heat transfer beyond the normal capability of water. So we are using also nanotechnology, nanofluids to investigate improved heat transfer. That's a longer-term research. The other aspect of this research was how can we build very thin liquid coolers, so that would allow a much denser spacing of future boards. So the current spacing, the most dense spacing of a board, is limited by the vertical dimension of the air heat sink for the processor, which is of the order of 13 millimeters or 1 U. While if you're building a high-performance fluid cooler, we can restrict that on a packaging level to 2 millimeters. Here is an example of such a system. We are having small channels So they're doing the heat transfer, and these are the capillaries, same dimensions of about 20 micron. And the length of the biological capillary is about 100 microns, so we're using also about 100 to 200 microns. We have now a more rectangular version of implementing that, has been recently published. So you see here an inlet coming from one side, cold water, and the outlet on the other side, and everything very compact so that the whole cooler doesn't need a vertical access here, it only needs lateral access, and the thickness is less than 2 millimeters. So we can really densify electronics in the future from 30 millimeters minimum to 2 millimeters minimum on a packaging level. So that was the first effort to really have higher, more compact systems. And as I said before, I'm repeating that, more compact systems save energy because the wires are shorter.